Okay, hi. Welcome to our Structures 2 media presentation. I'm presenting this on behalf of Group 1, and this is basically to reflect on the subject as a whole, but in particular the assignment that we've been working on for a number of months. The assignment was to design a domestic steel shed. This has proved to be a very challenging assignment. It's been a lot of work, but very rewarding. So I will basically just talk about what I've gained from this assignment personally. We will start with, I guess, the understanding that there are certain loads acting on structures. The loads that we have to analyse are dead loads, live loads, wind loads, earthquake loads. However, as we're not in an earthquake-prone area, we didn't need to look into earthquake loads. Each group was assigned different parameters for the design of the domestic shed. The parameters that our group were assigned, differing from the others, were a span of 6.5 metres, height of 4.2 metres, wind region A and wind terrain category 2. So we started by doing our wind load determination to get our design wind speed. Basically, we use all of these Australian standards. The ones used most for this assignment would have been Australian Standard 4055 and Australian Standard 1170.0, 1170.1 and 1170.2. So with our wind region A, wind terrain category 2 and topographic class with no shielding, we're able to determine that our wind classification is N4, so that we can get our design wind speed. Then we use the net pressure coefficient from the standard and use the equations in the standard to input our data to obtain our design wind pressure. The elements of a domestic shed that we then had to design, we didn't have to design the sheeting, but we needed to choose a sheeting and a thickness, a base metal thickness, and determine what we would be using: sisolation, insulation, are we using a ceiling, is there any air conditioning for ducting? All of these things we then needed to look up the manufacturer's design capacity tables to determine the self-weight of the materials so that we could move on and design our purlins to support these materials, and our girts, determine how many rows of bridging were needed. From there, we could design the bracing required for stability from lateral loads, and then we designed the rafters and any fly bracing that may have been needed and where to put that fly bracing. From there, the loads transferred to the columns, so we needed to design the columns to transfer the loads down to the footing and the foundation. Apart from a lot of hand calculations, we also used Space Gas software, in particular to design truss calculations for the diagonal bracing. but it was also useful in beam design. So it's been a great experience learning some new software, and even though I only have a basic understanding of how to use it, I'm sure I'll be practicing with it some more. From the determining the dead loads from the self-weight of materials used, the live loads and the wind loads, we can then from the standard determine our load combinations using the formula set out in the standard, so that we end up with our most severe design combinations, which is what we use to look up the design capacity tables from the manufacturer, depending on what member we're looking at, whether it be Z section, C section for purlins or girts, or universal columns for the columns, or universal beams for the rafters. Also, for the bracing, we used equal angles and square hollow sections for the struts. We were required to design the structure for wind loads from two different directions and determine the load paths, how the loads were transferred from the sheeting and whatever else was on the roof down through the purlins to the rafters and columns, and how the wall sheeting loads were transferred back up through bracing and struts and down again to the columns, or the lower half of the wall sheeting would be transferred straight from through the column to the foundation through the footing. So the most severe design combinations would be for an ultimate limit state and a serviceability limit state. The ultimate limit state would be the place where the structure would fail, and serviceability needed to be designed so there was no excessive deflection or cracking or vibration. The main thing with looking up the design capacity tables was to find a member that would fall under the required load capacities, but also be the lightest possible member for design efficiency and cost efficiency. However, sometimes you may use a larger member than required, just for continuity of design and ease of connectivity with other members. So to finish off, I guess I'll just reflect on what I have learnt in this subject and through this assignment. I've learnt how to use space gas. As it had been a number of years since I did Structures 1, I've had to relearn some of the stuff that I learnt in Structures 1. It's been rewarding, it's been very challenging, and it has extended me. But I feel confident now that I have a good understanding of how to design simple structures, and from an engineering point of view. I've also had to learn how to present a media presentation. Previously, we only presented in front of actual people. So thank you to my 12-year-old daughter for helping me with this. In summary, it's been very challenging, a lot of work, but at the end of the day, very rewarding, and I've learnt a lot. Thank you.